Okay, so in this video we'll talk about the fundamental theorem of calculus, which, as the name suggests, is a pretty important theorem, in that it unifies differentiation and integration, right? The two operations that you'll be learning about in calculus. So to begin the discussion, I'd like to first look at functions of this form where it's probably slightly different from the functions you're used to seeing. It's g of x is equal to the function defined as the integral from a to x of some other function f of t dt, where this function f is a continuous function on some interval a to b. Right, so notice here that x is your independent variable in this function, and what the function formula says is for every input x, say you can plug in a 2 for instance, then you evaluate the function value at 2 by plugging in 2 for x in the integral formula, right in that upper limit. And now you may probably think, well, why are we looking at this kind of function for? Now, if you remember, we've talked about areas under curves corresponding to the distance traveled by, say, a car or a particle if this curve denotes its velocity function. Right? So I can take, say, the area under this curve v of t in between 0 and some time b. And whatever this area is will correspond to the distance. And so you can think of this function a to x of f of t dt as representing the distance traveled so far, right? Starting at time equals a to time equals x. So just to give you a more concrete example here, let's take f of t to be equal to t. So it's this function here. So t is in the horizontal axis. This is your function f of t. And let's set a to be 0 so that the function g is the integral from 0 to x of f of t dt. Okay, so what does that mean? Let's compute a few values for this function, starting at, say, well, t equals 0 for 1, or x equals 0. When x equals 0, what is g of 0 equal to? Well, the function says take that value of x, which is 0, plug it into the upper limit, and evaluate the integral. And now, well, we know that if you have an integral where the lower and upper limits are the same, that integral simply evaluates to 0. So what I'm going to do here is I'm going to create a plot for x and g of x by plotting points. So when x equals 0, the function value is 0, so that's this point here. Okay, so how about at 1? So let me make some space here. So this is equal to 0. When x is equal to 1, now you're plugging in x equals 1 into this integral. And, well, what do we have here? This is just the area under f of t and above the x-axis from 0 to 1. So in our graph here, it's whatever this area is. And that area is equal to 1/2, right? It's a triangle with base 1 and height 1. So, well, I guess we need a scale here, so I'm going to set this to be 2. So this is 1, and this is 1/2. So the function value of g at x equals 1 is 1/2. And we can keep doing this. I'll do it one more time. Let's do it for 2. G of 2 is the integral from 0 to 2 of f of t dt. And it's this area here of this triangle from 0 to 2, which is 2 times 2 divided by 2, or exactly 2. That's a lot of 2's. But now we get this point on the graph. And well, you can kind of see a pattern here. In fact, we are able to actually get a formula for g of x in general for any x that's larger than 0, right? By just observing that for any x value that I use for the upper limit of g, so say I cut it off here and I pick this as my x, whatever this integral is simply this area right? So 0 to x of f of t dt that's always going to be a triangle with x and height x. Therefore, this is x times x divided by 2, or 1/2 x squared. Which tells me that what I was drawing here are actually points on the parabola. Y equals 1/2 x squared. And this is our g of x formula. Right? So that's nice. Because from this function, again, if you think of f of t as your velocity function, now you have an explicit formula for g of x that tells you at any given x, right, at any given point in time x, how far have you traveled? And, well, what do we know about velocity and distance? Again, if you take the derivative of velocity, you should get distance back. And in fact, that's exactly what's happening here. Right, so this was 1/2 x squared. What happens now if we take the derivative of g of x? Right, so g prime of x is the derivative of 1/2 x squared. And look, you get x back, which is just the original function f, right? Just written with a different independent variable or a dummy variable. And it's this statement here that corresponds to the first part of the fundamental theorem of calculus, right? Which we will state formally right now. So it turns out that if you start with a function f that's continuous on a to b, and put it inside an integral from a to x, and define a new function that depends on x in that way, as we did on the previous page, then this new function g, we know quite a bit about it. We know it's continuous on the closed interval from a to b, it's differentiable on the open interval from a to b, and also the fact that we ended with on the previous slide, g prime of x is equal to f of x. Okay, and you can think about it in this way, in the sense that if I start with any, so let's draw some axes here. If I start with any function f, right, so let's say this is my f of t, and I have an a, so I cut it off there. Well, at any given x, you can imagine dragging this vertical line to the right and changing the area that's being covered here, right? So when you move this vertical line to the right, the area grows larger. The rate at which that area is growing is exactly equal to the function f of t. And that makes sense because at any given point in time, you can basically imagine this as simply you're adding a bunch of thin line segments when you're moving to the right and increasing x. Right? So the rate of change of that area function when you're dragging x to the right is exactly f of t, or f of x, right? The function value where you're standing. Now, this part of the fundamental theorem of calculus also has some computational implications, in the sense that now whenever we are asked to take a derivative of any function with x for the upper limit, or with the independent variable in the upper limit, and some other number, right, or constant for the lower limit, say 5, and I can have any function here, e raised to t dt, then the derivative of this function of x is simply equal to e to the x. Right? You just take x and plug it into wherever you see t in that formula inside. And it kind of makes sense here that 5 does not really make a difference. I can change this to 5,000 and the result will still hold. It's still e to the x, in the sense because where you start, this a doesn't really matter. It doesn't really affect what the rate of change is exactly at x. And now, just to end, let's do another example now with something other than x in the upper limit. So say you had 3x instead, right? And you're asked to take the derivative of this function, integral of 1 to 3x, of 1 over u squared plus 1 du. Well, what would you do in this case? Well, the only difference is that, again, it's not just x inside, but it's 3x, right? So what do you do if you have a composition of two functions like this, right? So you can think of this as the composition of, let's see, I'm not going to use f, say g of x is 1 to x of 1 over u squared plus 1 du, and another function h of x equals 3x. Then that means you're just taking the derivative of the composition of, so which one are we doing first? We're doing the 3x first, and then plugging it into the upper limit. That means h is inside the composition. And we know that the derivative of a composition using the chain rule is now just g prime at h of x times h prime of x. And now you can just use, again, the fundamental theorem of calculus. G prime of h of x is what? Well, we know that g prime of x is equal to, since now we just have x on top, plug it in for u. This is 1 over x squared plus 1. So this is 1 over x squared plus 1, but instead of x, we're plugging in this h of x term, which is 3x. And lastly, we're multiplying by h prime of x, which is just 3. Right? And this really illustrates the following fact. If you have any other function here inside for the upper limit, aside from x, then you do the same thing as the fundamental theorem says. You take this whole function h of x, plug it in for t. Then you just have to multiply by the derivative of h prime of x, right? So that's the same thing as multiplying by the derivative of the inner function in the chain rule.